So I'm here to say welcome. So welcome to Sheffield. Very glad you've made it. One of the main things about the UKCCSRC conferences is the networking, and I'm glad to see that everybody was networking well and carrying on going until the very last minute before we meet. So that's excellent. We'll have plenty more time for networking, and it is often where the most valuable work happens at conferences, I find. Having said that, we've also got a very good set of speakers. We're having all the sessions in plenary, so you'll get to listen to stuff that you might not normally listen to. That's always good. Good excuse to have a nap anyway, if it's something you really don't want to listen to, but I'm sure it'll all be very good. And then, as usual, we've got the meal tonight when we can get even more work done. Have we got alcohol? Yes, okay, very good. We managed that. This is proving even harder at academic functions, but we do expect you to work hard, and we find that usually, for a number of people, lubricates the discussion. So, all good. Obviously, one of the things that's coming up now, I've been reflecting on what's different about our meetings, and I'm seeing it very, very forcibly, and I'm sure a lot of other people are, is that we're moving from CCS being something theoretical, as it has been for a lot of the, really in many ways, a lot of the 20 years that I've been in the business, to something that's really practical, with all of the interesting and challenging bits that brings in. So that I'm sure will be a good chance over the time to meet people who are actually thinking about this or doing it and actually starting to see some of the real problems. And that is something that I really hope we can get value out from this meeting is the discussions around actual problems, not just academic research, but also we will get some academic research that ties into those problems. So you're here to work, have fun, but do work hard, and remember the working hard is the networking.
Okay, good afternoon. So Mathieu Lucquiaud from UKCSRC and University of Sheffield. I'll chair our first session on CO2 capture. So without further ado, let's get Stavros in. Stavros Michailos from the University of Hull, who is going to talk to us about ultra-high capture rate and reclaiming, if I'm not mistaken.
The floor's yours. Thanks, Matthew. Yeah, hi everyone. Thank you for the invitation. And as Matthew said, today we'll be talking about ultra-high capture fraction in post-combustion plants, and also about thermal reclaiming, and finishing off with some economics. And John talking about theoretical. This is going to be a bit theoretical study. So the challenge that we try to deal with is effective operation at ultra-high capture fractions up to 100% of the added fuel CO2. And this is because successful deployment of post-combustion plants will predominantly rely on achieving these high capture fractions consistently. We will also be discussing about some designs of solvent management strategies. I say here solvent management, but the focus will be on reclaiming, basically to ensure durable operation, and in this way we can de-risk the project financing and long-term viability. As I said, theoretical study, so we did process modeling in the Aspen plus CCSI environment, and we extracted some data from a FIT study, the Sherman FIT study issued by Bechtel. We will be focusing on some key process parameters. We'll present some sensitivity analysis on lean, rich loading, liquid to gas ratio, intercooling in the absorber, temperature profiles, and the pressure in the desorber. These are nothing new, pretty much a typical outline process flow diagram of a post-combustion plant. What we've done is to examine its performance at lower lean loading that you usually come across in similar studies, and a slightly higher pressure again than usually at around 2.4 bar atmosphere absolute. The absorber, unless stated otherwise, is a 3-bed, or each bed of 8 meters or 34 meters.
It's not picking you up very well.
Now, now, better, right? Okay, brilliant. Now about the reclaiming is, sorry, can I? No. The reclaiming is a continuous operation, and we have either a single or dual stage. Okay, the first one operates at desorber pressure at 2.4 bar, and the second one at atmospheric absorber pressure. The vapor from the top of the first reclaimer goes into the stripper to recover solvent and energy, while for the last flush operation, the vapor goes to the absorber, while the bottom is going to the amine tank that can be served as solvent. As I said, we did some sensitivity analysis on lean and REACH. These results are for 95% capsule. Again, pressure stated again here 2.4 bar, and we tested the effect of lean on the SRD. SRD stands for the specific reboiler duty, and basically we wanted to see the effect that the REACH has. We want to design the absorber in such a way that we can maximize the REACH. So you can see the higher the REACH, the lower the SRD is. And this is because of the lower equilibrium CO2 pressure in the absorber. So if the REACH is low, we basically force the reboiler to work harder. And you can see on the left-hand side of this graph, this inflection point, lean loading below which the SRD exponentially increases. A bit more about this inflection point in this on this slide, where here we present also the effect of different pressures as a function of the lean loading. In this exercise, the REACH is constant to what we have seen that is a reasonable value of 0.45, and again for capsule 95%. The main reason that we operate at low lean is because we enhance the mass transfer in the absorber, okay, and we can overcome the pinch that is created at the top of the absorber, okay. So even at this stage, we can have absorption going on. The higher desorber pressure is beneficial in terms of the energy penalty. The temperature increases, so as the CO2 equilibrium pressure, which is what we want in the stripper, okay, because we can have better transfer of the gas from liquid to the gas phase, and we can achieve in this way the low lean. But the caveat is that we can go as lean as basically this graph shows, as basically the pressure allows us, okay. Below this point where the inflection takes place, it appears that all this excessive steam that the reboiler generates does not really accompany with an effective internal heat transfer within the stripper, which results much of this heat to be just wasted at the top of the desorber. So the key takeaway from here is that there are different pairs of effective lean loading and pressures. As you can see in this graph, the bottom side, the higher the pressure, the lower the lean that we can achieve, and hence, as we mentioned at the first point, higher capture fractions. And we have noticed that in all cases, this takes place when the water vapor over the CO2 strip takes place when it reaches this critical value of around 3.7. So we applied this design in multiple cases. I present here mostly about heavy industries that they work at high capacity factors, cement, steel, refinery, and energy from waste. But all the previous exercises have been conducted on CCGT flue gases. And we can see here the optimum value of lean loading for a pressure of 2.4%. And the gross capture in this case is 99%, not 100%. We'll talk in a bit why is that. And you can see that the optimum lean for all cases lies between 0.1 and 0.12, while the SRD is below 3.5, 3.7 for all cases. And this value is well within the range that has been reported for lower capture fractions of 90 to 95%. This is, I would say, this corner graph basically a high-level operational map, and we present here again the capture fraction and SRD and reach as a function of the liquid to gas ratio, a value that can be easily, well, relatively easily monitored and controlled in actual plants. And we have identified three regimes. Obviously, the first one where the flow is too low to capture enough CO2 can be considered infeasible because the capture fractions are way too low. In the middle, we have the optimum flow regime, okay, for a liquid to gas ratio roughly between 1.6 and 1.9, that we can achieve the high capture fraction of almost 100%, not quite there, but around 99 as we presented before. And in this case also, the reaches the optimum value of 0.45. Now, it's not very clear here, but we cannot achieve 100% for the cases that we examined purely with playing with lean loading and pressure within these ranges because these flue gases contain lots of CO2 and they generate lots of heat during absorption. So we do have two options to reach the 100%. Either cooling in the absorber or go even harder with push further low the low lean loading in the expense of further increasing the pressure in the desorber. We wouldn't want to do the latter one because we'll further increase the temperature and the degradation in the stripper. So we did intercooling. These are the absorber profiles for 99% capture. On the left-hand side, there is no intercooling, and you can see the actual CO2 pressure in the gas, the equilibrium, and the temperature of the liquid. I mentioned here is full thermodynamic. We cannot have much operation, even if we do have, in theory, more capacity to absorb CO2. So what intercooling is doing, as you can see on the right side, basically increases the distance at the top of the absorber between the actual pressure and the equilibrium pressure, allowing for mass transfer. Results about 100% capture. We'll be talking mostly later on, especially about the economics, about the energy from waste, or some input data about flow rates, temperatures. They've been universal across all studies. Okay, now the key outcome here is that 100% capture for a 24-meter absorber can be achieved again with relatively low specific reboiler duties for all cases, okay, below 3738. And specifically for the energy from waste, this is 3.6 and increased roughly by 5% from the 95% capture case. Then lean is 0.12 and the rich 0.46. Again, just to mention the 3.4 is for 95%, not the 99 as in the graph, sorry. Moving on, because we operate at slightly higher pressures, okay, we wanted also to examine the effect on the reclaiming, because we expect to have higher degradation, especially in the stripper. So we can work on this design, and we model it again in Aspen Plus. Okay, just a brief reminder, two configuration, one stage and two stage, which the first reclaimer operates at the desorber pressure. These reclaimers, basically they are reboilers, okay? They boil the solvent, and we want to recover as much of MEA at the first stage. It is a continuous reclaiming, and with a slipstream of 0.11%. I'm not sure if it happens. Yeah, over here in the hot lean, we can treat the whole inventory in 21 days. The degradation model was based on data, actual data, pilot scale data from TCM. And we have seen that the consideration of the degradation products and the heat stable salts was roughly 4.4%, okay, which was below the threshold of 5.74. I mentioned somewhere here, can we find that is conservative, or I want to believe that is conservative. First of all, about the oxidative products in the absorber, the oxygen content in the flue gas in the TCM was higher than ours. So we expect to maybe over-predict the heat stable salt formation. And also for the thermal degradation, we only considered HIDA to represent the whole amount, and HIDA happens to be the most volatile, which again means that we may over-predict the thermal degradation products as well. These are the results. We do also steam stripping. We can extract water from multiple stages within the post-combustion plan. Here we get it from the desorber, from the flash, from the reflux. Yeah, and we do steam stripping basically to enhance the recovery of the solvent. There's always a trade-off between selectivity and recovery, as in any separation, right? And we can see that by increasing the amount of water we produce, both MEA and HETA recovery rates increase. The higher MEA recovery was found for the one-stage reclaiming, but at the cost of very high HETA carryover. And if you notice here for the one-stage reclaiming, the top one, we produce more water for steam stripping, okay, which, to be honest, may distort the water balance of the capture plant. The two-stage reclaiming at 145 degrees achieve quite high MEA recovery, roughly an average of 90%, and substantially lower degradation carryover, between 23 and 32%. Now, about the additional penalty of reclaiming. Okay, we said through this configuration we can recover most of this energy. We present that here in terms of the equivalent electricity lost. Now, without reclaiming operation, this equals to 41.35 megawatts. Because the reclaimer operates at higher pressure, we need to extract a higher quality steam. Okay. For the desorber reboiler, 135, 3.15 bar, while for the thermal reboiler, 152, 5 bar, which obviously leads to different energy conversion factors. The bottom line is that the additional electricity loss is generally very low, okay, around 0.8%. So the overall electricity loss from 41.35 goes up to 41.7. Limitations, well, first of all, it's a modeling study. Okay, the thermodynamic model we used is not fully parameterized. I need to read from side. Yeah, parametrizes. Yeah, you got it. For the degradation mixture that we considered. On the other hand, the composition of this degradation product is quite low, so it may not affect a lot the results, at least at these rates that we were working. Potential degradation of MEA during the higher temperatures, operating temperatures in the reclaimer was not considered. We also considered caustic treatment to convert the heat-stable salts to sodium salts. And we assume that this happened at 100% efficiency, okay, with stoichiometric supply of caustic soda. And there is, again, no consideration of some potential side reaction of CO2 to sodium carbonate. Again, I mentioned at the beginning, solvent management, we mostly focus here in the reclaiming. So any other strategies such as acid wash because of ammonia formation is not considered here in the model, but they were taken into account in the following techno-economic assessment. We still believe that the trends are useful, okay, and they have informed and tested in a couple of pilot campaigns. Techno-economics, we conducted a discount cash flow analysis for the 100% capture, and we benchmarked it against the 95% capture. Okay, you can see here the capex, not much increase. Again, we don't have to oversize many equipment such as absorber and the desorber due to this lowly loading design. The solvent regeneration here also accounts for the reclaiming. Okay, the reclaiming itself accounts for 80% of this 21%, so roughly 1.6, 1.7% of the overall capex. OPEX and the levelized cost of capture. Some the electricity cost was assumed at 70 pounds per megawatt hour. The MEA 950 per ton. The waste disposal of the reclaiming at 500 pounds per ton. Again, the dominant is the electricity lost, and fixed costs, which include labor, maintenance, etc., comes second, while the MEA cost account only for roughly 5% of the OPEX. Now, the levelized cost of capture increases by roughly 4%, okay, from 78.5 to 81.5, which is not much increase, again, based on assumptions of the techno-economic model. This is a more complete breakdown of the cost. We can see the process is basically capex intensive, all right. Fixed cost account for 12, electricity 24 pounds, and the solvent management only 2.8 pounds. If we reduce the specific reboiler duty from 3.6 to 3 gigajoules per ton, which are some value that has been reported for other solvents, basically blends such as Caesar or proprietary solvents, the levelized cost will be reduced only by 3.5%, okay, from 81.5 to 72.6. And this does not include potential increase in these blending solvents due to increased solvent management cost. As someone will expect that, you know, a single amine with a low boiling point as MEA to have lower solvent reclaiming costs. We calculated also the marginal cost of capture from transitioning from 95 to 800%. Okay, how much it costs us basically to capture only this 5%. And for a 20-meter absorber, this is around 175 pounds per ton, while for the taller absorber is 141. And basically compare that with current DAX cost because they serve the same service, basically, right? Capturing residual emissions, which is much lower compared to current and projected DAX. Conducted also a sensitivity analysis between the reduction in efficiency working in higher capture fraction against the exposure to ETS of the waste plants. Okay, so basically the 100% capture, we have, well, gate to gate again, zero exposure to ETS, but reduction in efficiency, and this as a function of the CO2 price and the electricity price. And we can see that still, even narrow, there are some extreme market conditions that can make the 100% capture more cost effective than the 95% capture. You can see here for a very low electricity prices and very high CO2 prices, there is a narrow window that 100% capture can make basically more money. Conclusions, net zero again, gate to gate, is achievable efficiently with this design of pairing low lean loadings with increase dissolvent pressure plus intercooling for flue gases that they have a high CO2 content. Reclaiming, we presented some trends that can make our operation, the operation of the post-combustion plant durable with high MEA recovery and relatively low degradation carryover. And it is affordable, again, based on modeling and techno-economic assumptions. The transition from 95 to 100% should not be expected to increase a lot the overall capture cost. Okay, again, we don't need really big absorber than contrary to what we used to believe because of the operation at the lower lean loading. And also there are some extreme market conditions that can make the 100% capture more sensible in terms of economics than 95% capture. And I believe this is me. Yeah, acknowledgement to all the colleagues that have contributed, especially from Sheffield University, our industrial partners, SSC Thermal, Bechtel, Viridor, the DESNES, and obviously our funders, the UKCCSRC community and IDRIC. Thank you.
Okay, thank you very much, Stavros. Do we have any questions for Stavros, please? Are we doing the questions at the end? Okay, all right. In that case, let's move on to our second speaker. So, Dr. Daniel Mullen from SSE, who is online.
No slides online.
We going to try again?
Yeah, we're back to you, Daniel.
Right. Well, I'm not going to go into presentation mode because I've tried it about 8 times during John's conversation and it didn't work. So I'm just going to do it like this, which should hopefully be fine. I have no animations in my slides, so it should be grand. I assume you can see my slides. They're okay.
We can just as PowerPoint, yeah, not in slideshow. Yeah.
No, I'm not going to attempt it.
That's fine.
Grand. Right. Well, thanks for inviting me to this. Unfortunately, I couldn't be there today because our national infrastructure can't cope with high temperatures, which is worrying for the future. But we've Mel and John have kindly allowed me to do this virtually. So I suppose it's important to set some context on this, given the heat that we're experiencing at the moment. So this is just a slide I think shows the state of play. It's adapted from emissions gap report created by the IPCC, I think, in 2025. That's looking at how we're doing with regards to the Paris Agreement. And at a high level, it's basically stating that if we meet all of the current policies, if current policies continue and we continue or start to meet them, we have an 8% chance of staying below 2 degrees C. If you look at the more optimistic case, which is that if every single goal and pledge that has ever been made by every country in the world is met in full, we have that increases to a 78% chance of staying below 2 degrees warming. So I'll leave that to yourselves to think about if we consider that situation likely, but I don't. So I think it highlights the need for increasing ambition over and above what our most optimistic cases are at the moment. I work for SSC Thermal, which is a large-scale power generation company within the UK and Ireland. They are developing 2 large-scale CCGTs with CCS, one in Scotland and one in Humber. They're at basically feed stage at the moment and awaiting funding from the government as part of the track process, if we're still calling it track processes. I unfortunately don't have any update on those projects as of yet. But as Mathieu mentioned in the intro, I'm here to discuss a piece of work that was commissioned by the Energy Institute that SSE tendered for with support from Mathieu and John, University of Sheffield. And it's basically the scope was to develop a guidance note which will advise operators on the effects that introducing CCS to thermal power stations will have on its design and operation. So this is now being delivered to the EI and accepted for publication, with publication planned in the next, I think, maybe 2 weeks. So keep an eye out for that. And basically this presentation is a little plug for it. Just so that we're all, I suppose, on the same page, this is an extract from the report that's just looking at the key interfaces between a power plant or thermal power plant and a carbon capture plant or CCP. Most obviously, you have the flue gas going from your boiler, whatever, or your combustion source, be that a boiler or a gas turbine, via HRSG. So that's basically that carries the CO2 into the CCP. You, of course, have steam from a steam turbine used to drive the thermal requirements of the CCP. So that's usually low pressure steam. And you have condensate return to your steam cycle. You have a power demand to run the electricity requirements of the CCP. The two main requirements there is the compression and conditioning units and the flue gas fan, if included. Both of those are tens of megawatts is sort of the order of magnitude we're talking about, depending on for a 700 megawatt CCGT is about 30 megawatts or something to that effect. And then you have smaller loads in the megawatt scale for pumps and heat tracing and the like. You have a substantially increased cooling water demand on your system, so something of the order of 40% increase in cooling water demand, primarily for cooling down your flue gas from whatever the outlet temperature is, somewhere between 120 and 80 degrees down to 40 degrees ish, and for basic heat rejection in the system from compressors and the like. In your capture plant, you have a water requirement, so for makeup in your amine loop, and for your water wash in your emission control system. You have a couple of different sources of waste, so you will have likely have a blowdown on your flue gas cooler, that produces reasonably okay water, but it might be contaminated with things like with whatever's coming out of the back of a coal plant, but for a CCGT, things like ammonia from your SCR. So that's a waste stream. And then you have another waste stream from the condensed fluid from your compression conditioning system, and then the waste from your emission control system, which likely will include an acid wash. So you'll have an acid-based waste stream there. And actually, I just realized I'm missing the reclaimer. So there's also a waste stream from your reclaiming system that is fairly nasty. In a lot of cases, so I'll have to include that. As part of this study, along with the internal knowledge that we have at SSE and that John and Mathieu provided, we looked at the extent of the academic literature that's out there and 15 publicly available feed studies. So 8 natural gas studies and 7 coal studies that spanned 8 different amine solvents. They were all amine-based processes, quite a wide range of scale. So the 1.1 megaton to 8.5 megaton per annum scale. A wide range of CO2 concentration, so about 4% to 14% volume, and capture fractions from 85 to 95%. Unfortunately, there was no higher cases as of yet. And then we had 3 based in the UK, 1 in Norway, and 11 in the USA. So the DOE funded quite a lot of these studies, DOE even. Apologies for the wall of text for the next couple of slides, but I basically extracted some of the key insights that we gleaned while doing this work, and then tried to extract some of the keyer insights from that. So reading down in order, your steam supply, it was a big conversation topic for each of the feed studies, and most, if not all of them, looked at the trade-off between extracting steam from the power cycle versus independent generation of steam on site with a fired boiler or a combined heating and power plant. Some went for it, some didn't, but all of the feed studies fairly concluded that you can do a fired boiler or a standalone generation unit, but it will increase your costs, it will increase your footprint, and it reduces the net efficiency of the plant in most cases, especially if it's just a fired boiler. On the steam turbine side, if you're retrofitting or if you're designing your plant to operate with the capacity for unabated operation, you will likely have some inefficiencies in your LP steam turbine due to basically the fact that it's operating in an off-design condition, especially in the case of retrofits, unless you do a big reblading exercise. So that's something to keep in mind, and it can be multiple megawatts of efficiency losses in your steam turbine. On dynamic operation and flexibility, if we're looking at the independent steam generation case, so a fire boiler or a CCP, it does increase your flexibility because you can start that system up before your power plant does, say, and generate steam early. But it's also a notable source of reliability issues. So it's another point of failure in the system that can affect your reliability of your plant if that goes down while you want to operate your CCP. You don't have any steam. A lot of the feed studies included multiple train designs, so 2 or more parallel CCP design plants, which will increase your turnaround capacity, so you can operate at an extended load range, and also has sort of an inherent degree of buffer against reliability issues. So if one plant goes down for whatever reason, you can still operate at 50% capacity or more, depending on depending on how many trains you're running. Looking at, again, I suppose, trips and reliability, most of the feed studies cited the flue gas fan as a significant reliability and trip and hazard during a trip event, because if your flue gas fan trips, you very possibly will get a pressure buildup in your HRSG and back pressure on your GT that could lead to damage. So there has to be some capacity or some way to release that pressure very, very quickly once a fan trips. So fast acting dampers in your bypass stack is a common approach. Likewise, your ST could be at risk in the case of a CCP trip, because basically your steam supply to your CCP might back off, and then you get a massive increase in flow through your steam turbine, which could trip it. I already mentioned, but cooling duty substantially increased as a result of including a CCP, but that impact is reduced if you use steam extraction from your power system rather than having a standalone fire boiler, because you move the duty from your condenser elsewhere to the CCP effectively. So that can be mitigated somewhat that way. Flue gas extract. If we're looking at flue gas extraction, because all of these feed studies, I believe, were retrofits. Quite often they included long runs of ductwork, because of spatial considerations on the plant. They weren't built initially with the idea of CCP in mind, so it's basically not an ideal layout. That has a substantial increase on capex. That's been noted by quite a few feed studies and institutes, along with pressure drop in the run, depending on the route. It's, if it's a straight run, it might not be too bad, but multiple turns will increase the pressure drop. And a number of feed studies also cited that for retrofits, quite a substantial amount of work is required to allow extraction from the existing stack on the plant, if you can't tie in upstream of the stack. So there's quite a lot of civil works that needs to happen there, which would require your plant to be offline for. So it's again quite a big burden for a retrofit to be offline for that amount of time. SCRs very often will be required for CCGT applications, mostly because of solvent considerations, solvent degradation considerations. Not always required for your solvent, but very likely if there's if it's sensitive to NOx. Value engineering, modular construction is favoured to keep costs down and keep on-site time down. EGR, one of the studies included EGR, and they reckon that that provided value for money over the non-EGR case. And as far as we believe, Net Zero Teesside is implementing EGR, so obviously they see some benefit to it. Plate and frame heat exchangers offer space and cost and pinch temperature benefits over shell and tubes, but require shockingly regular cleaning and gasket replacements. That has a massive maintenance burden and exposure risks aiming to your operators, so that needs to be considered. Fogging over DCC can reduce cost and footprint, but you're limited by how much you can cool your flue gas. Basically, won't go down below the dew point and doesn't remove any impurities. I'll skip a few of these. Water washes, asher washes, dry beds, and demisters can obviously help to mitigate emissions. The actual requirement for each of those is very solvent specific, and is a function of the volatility of your solvent, among other things. And something that's probably not taught about very much, but is a consideration for planning, is that your flue gas will basically be 100% visible for most of the time from a CCP, because it comes out as saturated, whereas a normal plant comes out quite hot and you don't often see the plume. Flue gas reheating can mitigate this somewhat, but it's not a silver bullet. You will still have a visible plume a lot of the time. Last wall of text, I swear. Utilities, basically, they will increase quite dramatically as a result of CCP, not just electricity demand, but things like demineralized water, instrument air, telecommunications, and like I said, waste streams will all increase. Solvent management is a big consideration for implementation, and requires extended operational experience, as John alluded to ensure that that's well understood. Reliability, single point of failures are often highlighted as concerns, so the CO2 compressors and the flue gas fan, because they're often not spared and critical to the process. Flue gas bypass is often included in the feed studies to allow, if it's permissible, to allow the host plant to operate in the case of a reliability concern or a trip on your CCP. So you can just operate unabated, but your steam turbine obviously needs to be able to take the extra steam. Let's see. Online maintenance is very helpful. I alluded to the heat exchanger gaskets for your cross heat exchanger if you're using plate and frame. So having the capacity and the redundancy to do online maintenance can be quite helpful there. And corrosion is quite a concern in wet CO2 services, so corrosion monitoring is highlighted as being very important. Labour requirements was very quite widely between feed studies, but one thing that was highlighted quite often is that it's a different skill set than most power plants. It's more of a chemical facility rather than a power generation station, so it's different operator skill set. Waste management, like I said, the CCP will introduce quite a few different waste streams that may be more hazardous than is typically considered in power plant operations. And likewise, there's new hazards that are being introduced out with the hazardous waste streams, which is amines, CO2, fire and explosions. So that needs to be considered to put it in your design. As part of this, we also looked at trying to establish some way of predicting the footprint requirement for a CCP. This has been attempted in the past. I've shown two correlations here that is commonly used. On the left is what's advised by the EA, which is just to linearly scale it using a factor, and then there's a more complex calculation advised by in the decarb ready guidance for UK Gov, but you can see that they don't really provide a very good fit to the data, to say the least. So we looked at all of the feed studies that were available only for CCGTs, because that was where the most detail was available, and tried to generate a correlation based on flue gas flow rate into the CCP. So we looked at there's quite a high variance in the absolute footprint taken up by the CCP, but the idea is that the actual equipment, so if you take out spacing, the actual equipment should scale fairly well with flue gas flow rate, because they're all similar for CCGTs. They're all similar amounts of CO2 in flue gas flow volume. So we basically measured out all of the equipment space taken up by the CCP and scaled that with flue gas flow rate, and got quite a nice correlation. So a logarithmic correlation, and then apply a multiple factor to that prediction to get the total plant size. So it's sort of a plot to equipment ratio. So it's the ratio, basically how densely your plant is fitted to that within the space. So this is a suggestion for a new correlation that could be used for estimating plant footprint that we've put in the guidance note. We also did something similar for CapEx using the data that was in the feed studies, and basically bringing it all up to 2024, I believe, values, and harmonizing it and normalizing it based on location to generate a correlation that can be used with quite a pinch of salt to provide some sort of finger in the air estimates to the CapEx requirements, and it fits reasonably well with the data within class 4, class 5 accuracy limits. So that's basically a brief run through of the guidance note. It's like I say, it will be published in the next couple of weeks. There's loads more in it, but that's just a quick overview of what we've done. I believe there's going to be a panel after this, so we can ask me any questions then. Thanks very much.
Daniel. So it's basically 2 o'clock, so that's the initial end of our sessions. What I suggest we do is we take maybe 10 minutes from the break, 5-10 minutes from the break, and we have a 5-10 minute panel discussion now. So could have a Stavros and John. You come and sit at this table, and Daniel, if you could stay online, and I'll repeat any questions that is addressed to you. So yeah, any questions to Stavros or any questions? Yeah, well, maybe I will start. So I guess it is a question. It's, if you could pick one to answer challenge that from the work that you've done and presented, what would you be doing next, and what's an important thing that we would have to do next in terms of answering this question that you've got to get in there. So maybe Stavros, do you want to start, and then I'll have to join in Daniel.
Thanks, Mark. Well, yeah, as I already expanded, actually. Yeah, expand a bit from solid management strategy. So I think the guys also to calculate this example the reaction rate. Next high capture include acids, to model economics, and expand the values to power station. Playing with the business models that energy from waste could be exposed to ETS in a couple of years.
Yeah, it's one of the things I'd be quite interested in doing. Having spent long hours mossing notes with numbers on to try and plant operate. Sort of feedback control via pencil. It's quite effective, but it's very time consuming. I think it would be very useful to work with some of the data logging techniques which people like Mathieu developed, so you can actually get rapid feedback control and then implement it automatically. Thanks. So I'll be talking about some practical experience of getting high capture rates playing around in China. It'll follow on pretty well from Stavros's presentation. It was work that was also funded by SSE, particular tests, and UKCCSRC. So it's got a lot of the same links. And there's a lot of people there that have contributed towards this, people in the UK and people in China. Yang Shi will be one of the people who'll come along and talk to you tomorrow. So it's quite a large effort to actually get to do this, and you'll see why. We were using MEA. Why use MEA? Well, I'm not going to say a lot about it, but one of the things about it, as Stavros has said, is that you can reclaim it. And if you look at those two graphs, it's really to look at afterwards when you get the size. But the yellow bit on the top was the cost at these projects. Boundary Dam, first post-combustion capture project on coal in the world. Petronova, the second one. And the yellow bar at the top is the cost of solvent management. They didn't use MEA. They were having trouble reclaiming. And for a period of time at least, they spend a small fortune on solvent replacement. So MEA, although it's a bit old and clunky, is pretty good to use. This is just showing a circuit for post-combustion capture. Can you see that? So we've got the bits that everybody talks about, the absorber that captures the CO2 and the desorber. I call it a desorber, not a stripper, since I've been spending a lot of time in China. Stripper always gets mistranslated. So we've got these bits, and we've got the figure-of-8 circuit, the solvent going round, and that's all good. But actually, the most important part of it is over here, which is the reclaimer. And I was actually listening to a program on the origins of life, a podcast. And if you'll excuse the sort of the fairly basic nature, they said it was a absolutely critical thing when animals transited from being things like jellyfish, which just bring food in and spurt it out again, to being fish, because the fish have an anus and they can actually get rid of the waste, and they have a mouth at the other end, and you know, they go looking for food. And that's actually really a very, very important thing. And in the same way, if you don't have somewhere where you can get rid of the waste, you've got something that looks very good while it works, but it will sooner or later come a cropper. So ultra high capture rates, you've seen all this before with Stavros. Get a load lean loading, match the flow rate, and then also operate things independently. This is Stavros's diagram. This is it again, so I'm not going to show you. But I don't think Stavros showed this one, which is something actually that Daniel did. What we're looking at here is the temperature at the hot end in the reboiler. This is modelling. This is actually measurements on the NCCC test unit in Birmingham, Alabama. So this is the hot end, and then this is the top, where the solvent, rich solvent, comes in colder. And then what we're looking at is the temperature distribution as you go from the bottom to the top. And what you see is, as you make the solvent leaner and leaner, you pile in more steam, the temperature goes up and up and up, and then it flips, and that's the inflection point. And so if you're watching the temperature in the middle, Lucas is here, he's done a lot of work on this. I think Lucas coined the term dimensionless center temperature. If you watch that temperature in the middle, you don't need to watch anywhere else really. It goes from low to high, and it actually doesn't spend very long in the middle. In other words, it's quite sensitive. This is model, as I say, and this shows it actually happens in practice. So we had a fair bit of confidence that that would be the case. This is also just showing that you want to get a good rich loading. Stavros has done that. And this is showing this corner diagram on the left is just showing you've got a lot of trade-offs as you increase the capture rate, going from left to right. Your rich loading starts to go down and your energy starts to go up. So there's a lot of different things to do. Now, this is all very well. This is mostly modelling. We did get some data from NCCC, but they weren't getting particularly high capture rates. Can we actually do it in practice? And we don't have a suitable test unit in the UK anymore. We did have one at Ferrybridge that was built about a bit over 10 years ago now, but it got scrapped along with the coal-fired power plant. But China has quite a lot of power plants, and one of them in the south of China has a fairly large test unit built on it. It was built in about 9 months. Just shows how quickly things can happen. And it's been in more or less continuous operation ever since it was first set up. Testing, we managed to get a couple of weeks of time on it. It's down in the south, very nice place to visit, even at Christmas, where I was this last year. You can see it's dwarfed by the flue gas desulfurization unit. That's a seawater wash flue gas desulfurization unit. They claim the power plant's cleaner than a gas power plant. Stuff out the back end, it's got quite low NOx burners, sludge combustion, and so it's got a very good flue gas desulfurization. It's also burning pretty clean Indonesian coal. And then there's the capture unit. This is a model, but it really is that small. And then, Stavros, if you want to see a Chinese translation of what you were saying, it's there. This is me talking with the Chinese operators at the capture plant, describing the principles of operation that Stavros has explained in theory. And then this here is the bit where the rubber meets the road, or the steam meets the solvent. So this is the reboiler. And the solvent's coming in from the bottom. It's getting split up into a lot of smaller diameter tubes in this section, and then steam is coming in from the outside, somewhere up here, and it's getting condensed and coming out the bottom, draining out, and that's heating everything up. And this is actually quite important. You need a really large plant to have a realistic reboiler unit. I'll go on to the next slide if you remember that. This is a diagram. This is what we had. So we're taking the solvent out. The solvent's dropping down through the column. It's getting collected, and then it's going down, going into the bottom of the reboiler, getting evaporated, not all of it, but a fair bit of it, and then coming back in. And that's known as a once-through thermosiphon because that's what it does. It just takes the solvent once through. On most other test units, you've got other variations. It's easier to make them smaller. So here you've got a natural circulation thermosiphon. Here you've got the heating coils inside the unit. Here you've got another different variation on the thermosiphon. And these are all much slower, and they don't respond very quickly when you change the amount of steam going in. So they're harder to control. Here we are. On the left there is Wei Ming, who was the operator, who, when she told him what to do, was obviously really quite adept at doing it. He knew how to make his plant work. And what he's doing, we've got the control screen for the plant there, and we're trending various numbers. And the bits that really matter for controlling it are the temperature at the top, which is the bottom temperature, that's the high temperature, low temperature down here. And then Wei Ming's been controlling the temperatures very carefully to keep that light blue line in the middle with time. And it's active control. It's like riding a bicycle. You know, you ride a bicycle in the snow and you look at your track and you think you're going in a straight line, but actually your front wheel's inevitably wiggling. But it is keeping in very much the right direction. And that's what we're doing here. And then in 2024, which is when this picture was taken, we managed it for 6 hours. And then we went back Christmas 25, and we did the same thing for 75 hours, 3 days, continuous operation. And this is showing, again, it's this rough bicycle ride, if you like, but the top line is 100% capture, sometimes a little bit over, sometimes a little bit below. But it actually did achieve pretty representative capture. While we were doing this, the power plant was doing various messing around as burners were brought in and out. And then every once in a while, middle of the day, this was particularly difficult to cope with, actually, because I could get the operators to work overnight and they'd keep washing it. But I could not get the operators to work during meal times because they had quite a good canteen. I don't have a picture of the canteen, but it was really very good quality Chinese food. But if you turned up late, there was no food. You had to get the slot. So of course, 12 o'clock food time, that was it. And it usually just after we left, the CO2 content on the plant was changed as they went down to minimum load for the lunch break, I guess, when solar in Guangdong was getting up high. Anyway, we had these problems. We also had, as you can see, a sort of a bit of a furry line. Early on, the reboiler itself was oscillating due to changing condensate levels. It quietened down a bit later on. But basically, with all of these things, it was still a fairly successful example of manual control by doing the right things. Now, we've been modeling steady state, and you kind of assume steady state, and we're actually trying to hold the plant steady, but of course, as I say, things were fluctuating. And I'm not going to go into a lot of detail about it, but this is showing the blue line is the temperature at the bottom of the packing, so it's the temperature in the reboiler, and that's the impact of where you put the steam in directly. So that's the sort of the bit where you're driving it. And then the red line is this temperature in the middle. And you can do some cross correlation, and Aisha Ibrahim, who's here somewhere, I think, did this, and you can show that actually they follow each other as you'd expect them to, because it's related to the lean loading. Both are related to the lean loading, but there's 5 minutes between them, and that gives you some idea of the thermal lag in the system. It's a combination of the steam getting up there and just things getting warmer. So that's 5 minutes. Still relatively fast, and fast enough to do control. But then the next thing that really surprised me, and still does surprise me in many ways, is we're now looking at the difference between something over which we've only got limited control, which is the CO2 flowing into the absorber. That's the red line. So that's a function of the flue gas flow rate, which we were controlling, and the flue gas CO2 content, which the plant was controlling. And then the blue line is the CO2 coming out of the top. It's what we measured in parts per million. And those two agree, but the CO2 coming out the top doesn't vary for 20 minutes. Absolutely incredible. And obviously the residence time of the actual gas itself in the absorber is less than a minute. It's very, very short. But you've got so much solvent, this is what we think anyway, you've got so much solvent sitting around inside that absorber, and the solvent at the top of the absorber is really lean. It's actually acting a little bit like a packed bed. And what you're looking at is an analog to sort of CO2 breakthrough. So what happens when you put more CO2 in is that you don't immediately get it coming out the top. You don't change the flow rate. Flow rate's quickly enough to adjust. But you've just got lean solvent in there, and a little bit more of the solvent that's held up in the absorber just picks up CO2. And so in some ways it's a helpful thing, because it means that, you know, bad things don't happen if you fail to control the absorber itself buffers. But in other ways it makes life awkward, because if you don't realize that you're not going to see a result in the exit CO2 for 20 minutes, and you try and adjust the flue gas flow or the solvent flow, you know, you adjust it and you see nothing happening, so you adjust it a bit more, and you've overshot by the time you actually get a signal. So it's kind of interesting, and it's something we're looking at. And I'll sort of give you one possible solution. So this is now looking at, the red is in fact the captured CO2. This is based on the gas concentrations. And then the blue is the captured CO2 again, but it's what's come out from the desorber. So the red is what we're capturing from the flue gas based on the concentrations and the flow rates. And the blue is after it's been picked up by the solvent, gone all the way through the system, got cooked out, and has got to the CO2 delivery point. The other one took 20 minutes. This only takes 18 minutes. Who would have thought that would have been quicker? But it is quicker. And what that means is also then, if that's after it's been cooked out of the solvent, if you actually are able to look at the solvent coming out of the bottom of the absorber, that'll be somewhat shorter than 18 minutes. And that will actually tell you effectively what's going on. And also that'll be the rich loading, which affects the energy. So this is something that we've got that Aisha's developed. It's called the Ibrahim collector, and it's basically a gutter. So we've got here a tube cut in half going across with, in this case, a relatively small absorber at our plant here in Sheffield. This is the absorber poked in. This is sort of going away from you. And we found that actually, yes, you can see changes in the rich loading very, very quickly as you alter conditions in the absorber. So that's something we're looking to try out. And I have to say that surprised me that you can get quicker results in the amine coming out of the absorber than the flue gas. So, just as a summary, seems that what we got in theory you can actually get in practice with a few surprises. You do need to have a realistic reboiler. It's interesting that neither test centre Mongstadt, which gets a lot of airtime, nor NCCC have the right sort of reboiler. It does matter. And there probably are better ways to do it than we managed, but we did sort of manage it up to a point. And then going back to something I said at the start about reclaiming, the longer term plans are, now that we're reasonably certain that you can do the reclaiming, do the controlled capture, we're going to do that and come up with some better methods to do it. But you can show that works in a few weeks, really. But obviously on a real plant, you've got to keep doing this for years. And Mike Owensworth, who I can see there, sat in the middle, is going to take on the next bit, which is looking at being smart, in this case, solvent management at reduced throughput. And we're looking to go on industrial sites for realistic flue gas. And we want a plant that's small and cheap enough to run for long periods and to run tests in parallel, because you can't tell whether or not you can run for 24 months until you actually do it. It's very, very hard to infer anything from the short term. And if you realize that you've done it successfully in 24 months, you don't actually know that you haven't completely gone over the top in what you've been doing. You've reclaimed at a certain rate. Could you have reclaimed at half the rate? Well, how would you know? You just can't tell. So you actually want to be able to do multiple tests in parallel. And that'll be really important. And then also another factor, which I haven't got onto, but which is starting to vex people in the Environment Agency, and there's various people here. Gwenda McIntyre is there. If you want to find out about it, ask about amine-related emissions to atmosphere and what happens in clusters. And that's also obviously an area that we need to look at in a lot more detail, and hopefully come up with some pretty low levels for emissions so that the problem goes away. Okay, that's my bit. Shall I switch back to? We'll try.
Stavros and John, if you come in and sit at this table, and Daniel, if you could stay online, and I'll repeat any questions that is addressed to you. So any questions to Stavros, or any questions to John or Daniel, please? Okay, well, maybe I will start. So I guess it is a question. Is if you could pick one sort of unanswered challenge that from the work that you've done and you've presented, what would you be doing next, and what's an important thing that we ought to be doing next in terms of answering the question that you've left hanging at the end there. So. Maybe Stavros, do you want to start, and then I'll go to John and Daniel?
Well, as I said, expand a bit on solvent management strategy. So I think it would be nice also to calculate ammonia formation, for example, in the absorber for the increased high capture, include acid wash treatment into the model and the techno-economics, and expand the boundaries to the power station, in that case the energy from waste plant, and play a bit with the business models. The energy from waste will be exposed to ETS, I think, in a couple of years, 2038, so it will be nice to examine all these different business models.
Okay, thank you.
John?
Yeah, at least one of the things I'd be quite interested in doing, having spent long hours passing notes with numbers on to Chinese plant operators. It's sort of a feedback control via pencil. It's quite effective, but it's very time consuming and it keeps you up at night. I think it would be very useful to work with some of the data logging techniques which people like Aisha have developed, so that you can actually get rapid feedback control and then implement it automatically. Because I think there's things there that you can't see directly with your eyes, but they're there to inference from all of the different signals. And then I'd really quite like to sit there watching the plant steer itself.
Okay, and Daniel, same question to you. What? Give us one of these sort of unanswered challenge that you think we should address next.
Yeah, sure. I quite accurate in things that are successful. Apologies if I'm repeating myself, but the the way the business model in UK works for Power CCS is it's primarily funded through the availability payment, which has a number of factors in it, but it basically equates capture rate and availability as equally weighted in the payment, and which is fair enough. It's called an availability payment. So one of the aspects of that I worry about in development is the actual availability and reliability of this CCP. And the financial models will be developed based around extremely high rates of availability and reliability, and with very, very punitive penalties for not meeting that. And I think with our current level of understanding of these plans and the current level of investigation and long-term operation that we've done, I am personally concerned about meeting those targets. So that's something I work on quite a lot, and it's something I would like to see more of in focus, is the actual operation availability and reliability of systems.
Okay, thank you. I think we have a question here in the middle.
My question is for John. Have you found Mia as a perfect solvent for absorption, or are you planning to test any other solvent in the future that has good credibility as Mia?
Yeah, we should probably take this one over coffee, but very quickly, it's a little bit like, I think it was Winston Churchill said about democracy. So it's the worst government system you can think of until you look at all the others, and I think that's true about MEA. The critical thing about it, actually, that I believe, well, two critical things actually. One is it's a primary amine. But maybe it is the same thing. It's just got two carbon atoms, okay, which means it has to be a primary amine. But also, because it's a primary amine, it's just like ethanol, alcohol. You can boil it off, and you don't have to do anything very complicated. You just have to boil it. And because it's only two carbon atoms, when it degrades, you either get polymers, which are quite a bit heavier, or fragments which are lighter and have to be dealt with. So it's very easy to reclaim. You can, and I don't know of anything else you can reclaim. And also I think pretty much all of the advanced solvents, maybe not everyone, but the ones we know about, use secondary amines, principally piperazine, to get high reaction rates with low energy. And they all make nitrosamines. And personally, as a professional engineer, I wouldn't put anybody I was responsible for on a plant with secondary amines unless I knew how to keep the concentrations of nitrosamines at a reasonable level. And a reasonable level's, probably parts per billion. And what we're seeing reported is practically percentages. And that's just unacceptable. They may be a bit cheaper, they may not, it's hard to tell. But I just, I think it's the analog to a lot of other things. As we've become more aware of health risks of certain chemicals, even if they're nominally better, we just don't use them. We don't use carbon tetrachloride for dry cleaning anymore, but it's just the way things go. We don't use benzene for, degreasing bits of engineering plant. It's just the way to go. That's where we're at the moment. I could be convinced otherwise if we got some results, but we haven't seen published results that show anything better at the moment. That's where we're at.
Thank you.
Okay, question at the back there from Richard.
Hi, Richard Porter from University College London. I was just wondering if retrofits or brownfield redevelopments or new builds are seeming more favourable for power stations with CCS these days.
Who wants to answer that? Okay.
I got your question if it's being read, but I just
Did you hear that, Daniel?
Yeah, did you hear that? Okay.
Are retrofits, brownfield redevelopment, or new builds seeming more favourable for power plants with CCS these days?
Okay, Daniel. So it's a question about what's more favorable for CCS these days, brownfield, greenfield, or retrofits?
Retrofit's probably cheaper because you don't build the power plant, but absolutely by no means is every plant suitable. Likely, I alluded to basically getting the flue gas and steam to the CCP, so it very much depends on the location of the plant, and of course there's a massive footprint requirement. So retrofit, is a good value proposition if the plant can do it. Greenfield and brownfield, I mean, one of the massive barriers, like any new power plant in the UK is grid connection. So if you have a grid connection, you're really winning for building new build CCGT with CCS allowed. So at the moment very much depends on that. So I don't know if we can necessarily generalize. I think it's very location based. It's very dependent on if you have a grid connection with the utilities and at your doorstep, and then obviously actual access to a CO2 pipeline. So I think, I don't know if we could generalize on that.
Okay, thank you. I think we'll end here. So thank you very much, Daniel, John, and Stavros.